Bismillahirrahmanirrahim. Today we will discuss electrical safety. The first point is the mains supply, skin impedance, and earth. So we have 8 points to discuss. First of all, high voltage of the station is being transferred to a substation, decreasing the volt by a transformer. I think the station develops 11,000 volt, and then the substation transfers it into 240 volt in England and most of the countries around the world. So whenever it reaches the hospital, it reaches through 2 wires. We have the live and the natural wire. This natural wire is being attached to earth, you see. So the main electrical sockets in the hospital receives these 3 parts. So we will show you later on in a bigger diagram an anesthetist touching an apparatus, and there is a fault in the apparatus. So he is touching the live wire. So the circuit is being complete through him, where he is wearing non-anti-static footwear, or the ground has no sufficient anti-static floor specification. So the electricity is being transferred through him to the earth, returning back to the substation. So according to the current he receives, the sequely okay. So he may develop only 1 milliampere. Of course, this figure comes from the division of the volt, which is 250 over the 250,000 milliohm times 1,000 milliampere to receive the final 1 milliampere. So this will not do anything to him apart from some sort of tingling, you see. But if this current is high enough, where the current, the impedance is only 10,000, of course, whenever we divide 240 over the impedance, which is as you can see, instead of being 24,000 and be only 10,000, this will yield a figure of 24 milliampere, which will transfer from the head to the arm, passing by the heart in a period of a second, inducing ectopic beats and even ventricular fibrillation. Of course, the impedance of the human body, skin and tissue, is very minimal. Up to that, we can consider it almost nil. This figure, as we said before, it represents an anesthetist liable to be electrically coated. The other figure, we will show it in a bigger form, also as an anesthetist or whatever a personnel carrying an electrical equipment, and he is touching a field of saline, which is good conductor of electricity. And of course, this area has been earthed, where he is not wearing a proper footwear, or the floor is not well stabilized on anti-static specification. So he is easily to be electrically coated, and then after that, we must put in our mind that this 10,000 may be much less in circumstances where the affected person can have a needle or cannula, which makes the current goes easily. And of course, the timing of the ventricular fibrillation, of course, is increased whenever the current reaches around 50 milliseconds after the Q wave. This is liable for him to develop ventricular fibrillation. Of course, high frequencies are less affected by this current causing ventricular fibrillation, but low frequency, as you can see, in 50 hertz can induce ventricular fibrillation. Of course, the current also is easy to go through patient with myocardial disease and dysrhythmia. The current in the United States is only 110, and in the England 240, and most of the countries. This is why we ought to have a proper anti-static footwear and earthed anti-static floor, where the resistance must be from 75 kilo ohm till 110 macro ohm, 10 mega ohm. So a kilo and mega. This is important figure to memorize whenever you want to discuss how to protect the patient from electrocution. Now we come to how do we protect the patient from electrical shock. We must meet the international electrochemical commission standard 601. You see, to fulfill the proper method to guard against electrocution, where the equipments used in the theater are divided into three types. Equipment one, which is made of an isolator, and there is the main component in the middle, and you will see in the picture how does a shortage occurs when there is a fault. The internal component touches outer component, where the patient, where the anesthetist touches the outer part, which is live, where he can be electrically coated. This, of course, is being earthed. The method to overcome such a problem is to use fuses. Fuses, of course, are easy to melt by this high current. They also there is another fuse at the socket of the room. This is class 1 equipment. This class 2 equipment is simply reinforcing or doubling the insulator outwards of the apparatus. You see, the third method to overcome the problems of electrocution is using internally powered equipment, using batteries. Of course, the batteries will avoid the drawbacks of alternating current, but yet it could induce electrocution whenever the resistance is very low. Shock with earthed equipment. Of course, whenever I'm going to show it now. Whenever there is a fault in the anesthetic or the electrical equipment, the current can go through the patient, touching, suppose a bulb, the handle of a bulb. Through this part is being earthed, so simply he can be electrically coated, and the space blankets, which are made of metal coated plastics, used to control hypothermia, can be a source of earthing. Also, can whenever there is a fault in the electrical equipment, can be a source of earthing, and at the same time it will induce electrocution. This figure is not present in the new edition of Barbour, but is present the old one. I will show it later on, where we have what we call a neutral electrode. This neutral electrode, to avoid interference, is, as you can see, is not attached to the main component. It is floating, you see. So this is a method to avoid electrocution whenever I use a neutral electrode through this new type of electrical equipments. Of course, the capacitor present in the isolating, of course, circuits can represent another method where the current can flow. You know that capacitors easily can transfer very high frequency current than direct current, which is reverse for the inductor. You see, so whenever the circuit has, I will show it later, a capacitor, an isolated capacitor, it can be another route instead of affecting the patient, causing electric quotient. This is the figure showing the factory where it goes, the volt goes to a substation, and then the substation through two wires goes to the socket, as you can see, and the neutral is attached to the air, as you can see. And whenever the apparatus has a fault and the anesthetist is touching the live wire which is exposed, the current can go through the anesthetist to airs going back to the substation, inducing a current affection. This current affection, of course, may be 1 milliampere up to 24 milliampere, which is a lethal current. Of course, the patient is not wearing a proper footwear, and the anti-static properties of the floor is not accomplished. As we said before, we must have a resistor of 75 kilo ohm to 10 mega ohm. This resistance is capable to remove static electricity. The dissipation of electrical static electricity are being passed, but it will prevent current from going easily through the airs. This other picture showing the personnel carrying a fault apparatus. As you can see, the wire is being cut, and he is standing on a pool of saline. And meanwhile, he's not wearing a footwear, a proper footwear, and the floor, of course, is not it's not properly managed, and the water is attached to the pipe, as you see, where the pipe is earthed. So the circuit can go through this fellow back to the substation, inducing electric quotient according to the current. It may be very small, as we said, or it can be the 24. This is the class 1 of equipment to protect against electric quotient, where in case this is the insulator and this is the electrical circuit in the middle, and whenever faults occurs and the electrical circuit goes reaches to the case, as you can see, we call it shortage. This high current increases the temperature, melting the fuse, as you can see. So we have fuses in the equipment, and we have also fuse and at the socket. See, so this is the first method to avoid electric quotient by the class 1 equipment, which must be earthed. It is earthed. You can see that the case is earthed. The second type where we reinforce this insulator or double it. You see, so there will be no chance for the patient touching the outer part to be electrically coated. And this is a method how the earthed equipment can be a sort of passing the current through the patient. As you can see, the patient is sleeping, touching the stand of the electrical bulb, and this stand is attached to the atmosphere, and his feet is adjacent to the stand, and then there is a fault in the electrical equipment, so the current will go through the patient, reaching the earth back to the substation, inducing electric quotient. This is the isolated capacitor, not present in the new the generation of Barbon's book, where we have a capacitor present outside between the patient and the earth, as we can see. The capacitor it represent another route for the current to go through. You see, whenever we said before there is a fault in the neutral plate, or if it is attached, the current can go back to the substation through the patient touching an earthed equipment. But here the component which has a capacitor, it's outside, or it is the second part of the total system of the CERMI. So this is how to avoid electrocution by using what we call floating circuit out or isolating circuit. This is the method where there is no capacitor. You see, there is no capacitor. And these are the electrode, the neutral addition neutral electrode, which was attached to the case of the equipment. As you can see, this case is being earthed. So whenever there is a fault, we are doing this, of course, to avoid interference. But if there is a fault, easily the current can go through the patient and the earth completing the circuit. But nowadays, it is floating. So the electrode is away from the earth, as you can see. So this is present in modern equipments. Now we go back to our PowerPoint. We go to the second slide. Microshock, which is very important. What is the meaning of microshock? Ventricular fibrillation, it represents the total current going from the foot, from the head to the foot, with 24 milliampere. Only a small fraction of it reaches the heart, inducing ectopics and ventricular fibrillation. So this current density, very minimal amount, can be induced by intracardiac casters. Whenever there is a mistake, you can see from this small diagram, there is a mistake in the electrical equipment using casters, intracardiac casters. You can see that the patient is touching the stand of the lamp, and the current here is being breaking down. So the current can go through the intracardiac caster, whatever it is, an esophageal temperature or a pacemaker, whatever can go, and the patient can transmit this current through him and through the stand to earthing with a minimal amount of current. You see, you can use a current of 150 microampere inducing ventricular fibrillation, because this electrode or this caster is touching the heart. So you have a very minimal amount of current which can affect the heart, inducing ventricular fibrillation. So this is how a micro shock occurs. Of course, the risk is common with low frequency, and not like the direct current. And as we said before, we have a leakage current. Leakage current is a current which can be released from any electrical equipment having inductors and having capacitors. You know, all these circuits are liable to induce a current. This is a nice figure where how the anesthetist can induce ventricular fibrillation to a patient accidentally. See, this is an electrical equipment where we use casters. This caster has been transferred internally to the heart, and there is a fault in this apparatus. And the anesthetist is touching the patient, and his other hand is touching the electrical equipment which is earthed. You see, so the minimal current that can reach 150 microampere can affect the heart through a very minimal area touched. You see, so this is the color, what we call the current density. Though the anesthetist is touching the patient, he's not much affected because he only receives the 150 microampere, which will not he will not be aware of it. So this is how the anesthetist can induce microshock to the patient. Of course, the probes used in intracardiac as the esophageal temperature, which is being used behind the heart, can be a source of microshock. Nowadays, whenever you are asked to receive an electrical equipment, you must check its leakage current. As we said before, leakage current is current that is being released from the presence of inductors and capacitors in any electrical equipment. Of course, this current is very minimal, but it can affect, as we can see before, that it can induce ventricular fibrillation in catheters reaching the heart. So we have two types of equipments. We have equipments being used in cardiac surgery. We call it cardiac floating. I will explain what I mean of floating circuit. This circuit must have a leakage current be under 50 microampere. You see, 50 microampere, and we'll never forget the 150 microampere. On the other hand, we have equipment not used in cardiac surgery, which we call it B or B floating. The leakage current can be used up to 500 microampere. So these are the standards that we must realize during checking apparatus reaching to our hospital. Now we come to the last point, which is the cardiac pacemaker. Cardiac pacemaker, we have two types, of course. We have the first one is temporary, where we go through the subclavian and neck veins through the X-ray control, and we induce electrodes touching the heart, inducing a pulse. This pulse is under 4 volt and for 1 millisecond, inducing pacing. You see, or for longer period, we use a cardiac surgery where we insert a battery and electrodes embedded in the myocardium. Most of the recent defibrillators are called the demand mode. Demand mode means that the stimulating electrode has a second function. It can sensitize the atrium of the ventricle for its contraction. So if it realizes that the patient wants, the heart wants to contract, it stops and makes the heart contract. So this is the problem whenever we are using electromagnetic field rays. This used in, of course, in ovens or a diathermy and other equipment. These are dangerous in patient having a pacemaker. Of course, it's better, as we said before, to use a bipolar instead of monopolar diathermy. And the point is, of course, as we said before, nerve stimulators and magnetic resonance imaging and equipment for physiotherapy. All these are factors that may interrupt or deceive the diathermy, the pacemaker, the demand type. This is why whenever we have a patient subjected for surgery, where he has a pacemaker, we ought to use only bipolar, or the patient can go to his cardiac specialist to change the mood of the pacemaker to be constant type. The meaning of constant type that it will give a rate irrespective of any changes of the surrounding. The last thing I want to remind you is what we call the floating circuit. Floating circuit is a circuit where the electrical component where we have the electricity and the earthing is in a part, and it is separated by a barrier, most probably it's a transformer, from the part reaching to the patient. So we have two parts. This is a figure of what we call floating, where the main supplies out of the range of the patient. You see, they are separated from each other. We have two parts. This is what we call the floating circuit. And this is what we said before. This is a patient where a catheter is reaching to the heart, reaching to a very small area. So the current density is very high. So 150 microampere is capable to induce ventricular fibrillation. So there is the fault here, as you can see. The current will go through the patient, through the stand of the bulb, earthing, and in completing the circle till it reaches the substation inducing ventricular fibrillation. And this is where the anesthetist is touching an earth equipment, and he is touching but at the same time the patient, and there is a fault in the electrical equipment through the catheter reaching the heart, is touching the heart. So this fault can be utilized through the earthing induced by the anesthetist, causing ventricular fibrillation. You see, this is micro shock. And this is the maker. This is the long-term type where we we make a open heart surgery where we implant the battery, and the electrodes are being embedded in the endocardium, whatever it's atrium or ventricle. Of course, it senses also the capability of the ventricles or the atrium to contract, and it stops and gives the heart chance to contract. So they are affected, of course, as we said before, from electromagnetic equipments as the thermy and electrical. I hope that I accomplished my mission. Forgive me for my mistakes. Wassalamu alaikum wa rahmatullah wa barakatuh.